Okay, guys, it's kind of time to do a little summary because complex integration gets kind of complex. It seems to have a million paths to take. And having a conceptual basis for how you attack integration is a really important thing. So when you were doing integration in Calc 2, you learned all these techniques, integration of trig sub, integration by parts, integration with partial fraction decomposition. What you're going to discover that in complex, it really boils down to forms of Cauchy theorem and a couple other different forms. So let's just do a little quick recall. We can start with the integral over some path gamma of a function, and basically you parameterize on the path, and you can do it. And it's not necessarily nice. And an example you should be able to do is like the integral from I to I plus 2 of z bar on a straight line from I to I plus 2. And that's not too bad, and that uses that. Now, z bar is not a holomorphic function, and that means that any of the future theorems doesn't help. That's about the only way to do it. Now, when f of z exists, then all of a sudden something like this becomes easier. It's like the fundamental theorem of calculus, but z bar isn't that kind. But if we have a function f and we have a gamma, well, then it becomes the simple difference of the endpoints, and this is just wonderful. And a consequence of this is if you have a closed loop, then the answer becomes 0. So that's really nice. But you need the function to be holomorphic inside of this whole area here in order for this to happen. And the fundamental idea is contractibility to a point or independence of path, things of that sort. Now, something else happened in regions like this is that we could have one path and we could have a different path, and because that loop was equal to 0, then these homotopically equivalent paths of a function produce the same integral. This is really nice. Now, once we had done a couple integrals, we had discovered this one fundamental integral seemed to produce 2 pi I when we went around a circle. In fact, I'm going to start using the following notation that I want to go around a circle, and that circle is going to be centered at W here, so this is frequently called the winding number. And I'm going to show an application of this right now. I'm going to demonstrate how this integral counts how many times you go around, and you get a multiple of 2 pi I. In fact, if you put the 1 over 2 pi over here, you get 1. If you go around once, if you go around twice, you get 2. So let's do one of these. Let's take just 1 over z, and let's the path be like this. We're going to go around and around, and then right to there. So this is our gamma. It's going to go wrapping around the center twice. Now, how am I going to do this integral of 1 over z? All right, so I want to do that integral over that funny picture that we go around, and that's our gamma, and here's the origin. And I want to do the integral of 1 over z on this funky gamma. Well, what I'm going to do is I'm going to take this intersection point, since this is a continuous and smooth closed curve, it exists. So gamma 1 is just going to be this piece that comes to there, and then gamma 2 is going to be this piece that comes from there. And so this integral will become the integral over gamma 1 plus gamma 2 of 1 over z. And then it will be integral of 1 over z gamma 1 plus the integral of 1 over z gamma 2. But each of these is a 2 pi I because each of these are homotopically equivalent to some perfect circle that goes around there. And so here's a circle centered at 0, some radius r that's small enough, and C0r is homotopically equivalent to gamma 1, and it's homotopically equivalent to gamma 2, which means that we get twice 2 pi I. This is actually called the winding number of this problem. What's happening is this problem is really doing two things. It's evaluating an integral, but it's also counting the number of times that we are going around that 0 for the function 1 over z. This is frequently referred to as a winding number. All right, so now let's apply a very cool process. When we were proving Cauchy's integral theorem, we did integration and limits and of that sort. What would be very interesting is, since this formula is producing, as w's are fixed in this integral, produces f of w, well, now think of w in this context as being a variable where z has been completed. We might be interested in a derivative. To calculate using integration a derivative, it seems like it should be doable. Well, the cool and very powerful result, very powerful. And you can look at the page 73 and 74 where they walk through it. It's not very difficult. I'd like you to read that. I want to get to the examples because that's the really important part here. The very cool thing here is ready? A power comes in. And if we do it one more time, another power comes in, but a 2 went here. And so now I can think you can see the pattern. The 1 came out in front, it wasn't there. But when the went to the 3, a 2 went out front. When the 3, a 3 comes out in front. In fact, you probably can guess that's going to be n plus 1. What we've just discovered, and there's absolutely nothing like it in the real plane, and that is once a function is holomorphic in a region, and we can do this integral, then the resulting function f evaluation is the integral, but we also can prove that that function is infinitely differentiable. And there's a consequence for this. It starts proving that the partials and second-order partials and third-order partials of the function when expressed as u of xy, nu of xy, they're continuous. What's happening is this function that's being called holomorphic in a region is infinitely differentiable. It's a wonderful thing that happens, and it's amazingly powerful. But we need to remember, this is important, all of these pictures have a W, and there's gamma going around it, which is our circle, but we have a region of holomorphism for F. F is holomorphic in their entirety, so that's required for this problem. The numerator's got to be a nice function. Then, once it's nice, it's infinitely nice. This is a really neat process. Now, let's do an example of how this could come into play. I'm going to combine a couple of our techniques that we just did, not trying to make this hard, but demonstrate how each portion of what we've been learning is so powerful. So I'm going to start with the function g of z equals sine of z, and let's do it over z minus I. Now, this function is very nice, except it is messed up at I. But the function sine of z, this is holomorphic everywhere. So this is a very nice function in top, so almost no matter which gamma I give you, something interesting is going to happen. Well, let me just take a path. Here we go. This path wanders around this function. And let's ask ourselves, what should we do with this? Well, first off, this region that this is holomorphic in is everywhere, so I can put a disk around here. Centered at I, let's say of 1/2. Now, what's neat about this is we now can do the integral of our g of z over this path gamma by saying it's the same as the integral around I 1/2 of sine of z over, oh, I meant to do square here, I apologize, over sine of z minus squared dz. And now I go, oh, that's just a simple circle. It's centered at the place which causes that to be 0, and that's an analytic function. Therefore, the answer to this is f prime of w, and there's not a 2 pi over here, times a 2 pi I, and w is I. Well, the derivative of sine is cosine I, 2 pi I, and just like that, we have determined a value for the function by evaluation and a derivative. Now, I want to introduce another technique here. I want to introduce a technique that's extremely powerful. And so I'm going to do, let's do sine of z over z squared plus 1 integral. And I'm going to do it over a region that's pretty darn big. Let's make this big circle here, gamma. And here is going to be the number I, and here is going to be the number minus I. And so first off, I want you to notice that we have this idea of insideness. That's because we go around a closed curve counterclockwise. To the left are the points inside before we hit the function again. So all of this is inside, now outside. And so this region is the inside region. I want you to notice the two numbers that make this function bad are known to us. They are I and minus I. Now, I could do partial fraction decomposition, lots of things like this, but I'm not going to. I'm going to come up with this cool trick that is useful for doing this problem. What is this cool trick? This trick is the following. I am going to define a cut here. So this is going to be gamma 1. Going this way will be gamma 2, and going backwards there will be gamma 3, and finish going around there will be gamma 4. This means that the closed path gamma is now gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. And we know that the integral, this function, there's nothing wrong with it in that region. That integral is 0 on gamma 2 plus gamma 3. So therefore, the integral on gamma is going to be the integral of gamma 1 plus gamma 4. So this integral is the integral on gamma 1 plus gamma 2 of sine z over z plus I, z minus I, plus the integral of gamma 3 plus gamma 4 of sine z, z plus I, z minus I. Now, what's really neat about this is the first integral is just up here. There's only one bad point. So we'll move everything else to the top. And in the bottom, we put z minus I dz. And so now we have a analytic holomorphic function in the region that we're integrating. I, well, we're going to make this guy have a circle centered at I of some small enough radius to fit inside of there. And then by the Cauchy theorem, this is just going to be this function, sine of I over 2I times 2 pi I. That's that integral value. Now this one, that's this integral. And so we do the trick this way. We put the sine z and the z minus I in the top and the z plus I in the bottom. And this is gamma 3 plus gamma 4. We're now going around the bottom, so we use a circle centered at minus I of some very small radius so it fits inside of this picture and inside of the gammas. And we know that this is analytic because its only difficult spot is up there, but we're nowhere near it because we're down here. Therefore, this integral is the evaluation of sine at minus I, minus I, minus I, times, and now the 2 pi I. So just like that, we were able to calculate this integral by just doing some little trickery and this cool part of breaking paths that don't go around just one trouble spot, but more than one, into paths that just go around it once or twice if we had to. This is a very, very powerful idea. It's important to realize that the first integral had a region of holomorphism up there, where the only difficulty was I, which was centered at I, and the second one had its region of holomorphism down here, and that was for this function and this function. This function stayed away from minus I, therefore it was a homomorphism, and we could use Cauchy's theorem. And this function stayed away from I, therefore this one can do. All right, well, that's pretty cool. So let's, and every good mathematician probably can make a problem harder, right? So let's make it harder. Okay, I'm going to follow page 74, but it would work almost with any numbers that we put in here. This is a very simple concept once you start seeing how we're doing this. Let's do the integral over a circle centered at 0 of radius 2 dz over z squared z minus 1. Now, I want to point out that circle is not actually going to be that beneficial for you. It just identifies your initial path. We're going to have to create other circles in order to apply the right Cauchy integral theorem. So let's draw a picture. So first we put in the complex plane, identify the origin. We observe that 1 and 0 make trouble for this. And we observe that our gamma is right here. And we're always assuming counterclockwise. We're going to start writing this notation for going around a circle. So going counterclockwise around some circle of appropriate size. That's what this integral can be rewritten as without this. It's assumed to be nice. Now, we can do this by parametrization. We can use a Cauchy's integral theorem if we can get it down to the pieces we want. Well, obviously, using partial fraction decomposition, there's some A, there's some B, and there's some C, and this integral is in 3 parts. And this one will make use of the Cauchy theorem if we get the right path. This one will make use of the extension to Cauchy's theorem because it looks at like an evaluation of a derivative. And this one will be Cauchy's integral theorem normally. And we just have to observe that the a, b, c, and tops are going to be constants. Therefore, the numerator is a holomorphic function in the entire plane. But I want to use my tools. I mean, somebody gave me a power tool. I want to make use of it. So what am I going to do? I'm going to use this slice and dice one, and I'm going to pick a very nice path someplace between here to go up and down. And I'm going to call this gamma 1 down, gamma 2. Here's, I'll make gamma 1 start from here to there, down. And there's this, from here will be gamma 3, and then up will be gamma 4. So here we go. Gamma 1, gamma 2, gamma 4, gamma 3. Kind of silly. But, here we go. The integral over gamma 1 plus gamma 2 of dz over z squared z minus 1 plus the integral over gamma 3 plus gamma 4 of dz over z squared minus times z minus 1. We use the same trick we did before, moving things in the top, and we keep the appropriate part in the bottom. So here, since gamma 1, gamma 2 has the 1 inside of it, we'll put 1 over z squared, z minus 1, integral. And now I'm going to use this path is homotopic to some smaller appropriate circle centered at I, centered at 1, like 1/4, let's say. And now, what's the answer? Well, the answer is this is an analytic function in this region. Therefore, the answer is just that thing evaluated at 1 times 2 pi I. So that one's done. What about this one? Well, this one goes around 0, which is the denominator, z squared. So I write it as 1 over z minus 1 over z squared dz. And this is the gamma 3 plus gamma 4. And again, this is the path. So I'm going to make it homotopic to some small circle centered at 0 of appropriately small radius, let's say 1/4. Now this function is homotopic in a region that completely contains that because we've stayed away from its troublesome spot. But this is a second power. So Cauchy's extension theorem says this answer now is going to be f prime evaluated at w times the 2 pi I. And so I have to take the derivative of 1 over z minus 1, which is minus 1 over z minus 1 squared. I have to evaluate it at 0 and then multiply it times 2 pi I, and I get minus 2 pi I. So lo and behold, these two actually add up, and this integral becomes 0. The fact that it becomes 0 is not really relevant here. It's just I did the integral pieces part. So we use Cauchy's integral theorem on one piece, we use path subdivision on another part, and we use Cauchy's extension theorem on another. This is really an amazing process. We have brought ourselves to the point where it is doable to look at problems and to use small techniques for us to be able to advance our attack on them. So now, on page 76 in the book, we talk a little bit about how when we have integrals that we can draw certain conclusions. And I just want to reference Morera's theorem, which says that if you have a continuous function in a region in the complex plane, and its integrals on all the loops are 0, then that actually proves that the function is holomorphic or differentiable. This is a very strange theorem. It simply says continuity and integration of certain values produce differentiability. And that doesn't really have much like it in the real plane. All right, so now we're going to do a application, just one simple application of a pretty interesting problem that happens, and that is the complex integration process and complex calculations actually prove things that are really neat that we didn't realize. So one of the things you did in calculus is that you discovered if you had an odd-degreed polynomial, it had to have a root someplace. So if it's odd degree, then p of x has a root. Well, wouldn't it be nice to be able to factor every single polynomial? In fact, what we've discovered is you really can't. In abstract algebra, you discover that there's not a formula for a fifth-degree polynomial because it turns out the roots are very difficult to express. They're of strange forms. They're not what you expect. So the theorem that we're going to prove here for polynomials is really interesting. So we're going to take p of z, a polynomial, and its degree, we're going to make it, we'll call it d. Now, what we're going to do is we're just going to write that p of z is really just the sum of the ai, z to the I equals 0 to some number d. And then I'm going to take the modulo of this and observe that if I can do the following trick. First, I'm going to pull out z to the d from this expression. And so that means I am going to force powers in the bottom. Now this is very useful because we like things in the bottom to be large, and therefore their values get smaller. So now I'm going to do one other thing. I'm going to take the highest degree term out as well. And so these are now a sub i's all divided by a sub d, all divided by z to the d minus I equals 0 to d. This is nothing more than the following. It's 1 plus some new coefficient over z plus some new coefficient over z squared all the way down to some last coefficient over z to the d. So now, if we let the modulus of z get larger and larger and larger and larger, then each of these moduluses will shrink down and they'll go to 0. So as z goes to infinity, the modulus of p of z heads towards this value. And in calculus, this basically simply says that we are controlling the exterior shape of a polynomial by the leading coefficient and its degree. Quadratics far to the right are curving up or curving down. Cubics far to the right are curving up and curving down. And what happens in the middle is we're not so interested about. So when a limit exists, that means we can bound it. So let's look at this limit and say, since this is going to 1, oh, it's definitely less than 2, but it's greater than a half. So I can draw the following conclusion, that this a of d, z to the d, which is the modulus of p of z, it's going to be less than or equal to twice that, because we did a limit process, but it'll be greater than or equal. And now let's take 1/2 is smaller than the limit of 1, so it's 1/2 times the modulus of this stuff. Now, this seems like an odd thing to write down, but it simply says that the polynomial for large enough z is contained between very specific degree d polynomials in z for large values of z. Now, how can we use this? Well, we're going to do the following. We're going to do an integral. So, let p of z be given of degree d in the complex plane. And let's calculate the integral of 1 over the polynomial divided by z dz in some circle of radius r. Now, this circle goes around 0, which is the number that that's centered at, and 1 over p of z. Oh, is that an analytic function? Well, let's assume it does. Let's assume there's nothing that makes it bad. So assume 1 over p of z is a holomorphic function outside of z equals 0. So in other words, in that region, it's for some region r. So what's it mean? Well, that means that this answer then would be the evaluation of that at 0 times 2 pi I. Huh. Well, let's make use of this inequality. Here we go. We'll make use of that inequality. We know that 1 over modulus of 1 over p of 0 is 1 over 2 pi, the I goes away, times that integral of C of 0r, 1 over z, p of z dz. We're writing it this way. And now we're going to use the ML theorem. So this is going to be less than or equal to the maximum of 1 over z, p of z on the circle, times the length of the circle, which will be the 2 pi r. And this is the modulus. But we know how we had just bounded the modulus before with our inequality. And so now we're going to put in that a of d z to the d. And so this will now be less than or equal to a of d with a 2 in the top and a r to the dth power. It has that large value of d. Well, this doesn't have anything to do with the radius r. We just assumed that it had no root and that we could do that integral. And the answer is it's less than this value, which is the constant in the function, but any power of r that we like. Well, this gets smaller and smaller and smaller for larger and larger r's. And we said it didn't have a root. So that means 1 over p of 0 equals 0. And that's a contradiction. So what does this mean? It means we can't assume that p of z has no root. It leads to a contradiction. So every polynomial of degree greater than 1 in the complex plane has a root. And then you do long division, which produces a smaller complex polynomial. The consequence of this is that polynomials in the complexes are guaranteed to completely factor. This is amazing. This is a very powerful statement. Next time we're going to pick up on Liouville's theorem and take it from there.